Hi, in this video, we're going to take a look at partial factorial design of experiments. Okay, so we're in the situation that I wish I could have more data. And I'm going to be doing experiments to get data, but because of budget concerns, because of time, effort, logistics, whatever it is, I'm not going to be able to get tons and tons of data. So think about like scientific experiments or maybe experiments in engineering where I need to make every data point count. All right. So imagine that I've worked out the budget, how much it takes to run one experiment, and I know this, I'm going to come up short, but I still need to proceed with my experiment. What do I do? How do I get the most bang for my buck off of this? Well, I'm going to propose to you to use partial factorial design of experiments. Okay, what we're going to do, our framework, is that my ideal is going to be a full factorial design for all the variables of interest with all the interactions I could possibly have. That's two-way interactions, three-way interactions, four ways, whatever is applicable to the situation. That's what I would like to have. If I could have Santa Claus bring me budget and time, that's what I would get. But unfortunately, that's not the case. So what we're going to do, we are going to pencil and paper the mathematics of some abstract algebra to make sure that off of fewer observations, I get more bang for my buck for my experiments. Okay, so when we go and we do this, we're going to take some axioms to work with. All right, so I misspelled a word here, but that's all right. We're going to keep on rolling because my background's in math, not English. All right, first and foremost, the number one axiom is that the main effects are the most important and most interesting aspects of the experiment. Second, interactions are less interesting than main effects. Higher order interactions are less interesting than lower order interactions. And the intercept is always present. All right, so as I set this up, to make things easier for me to interpret, to keep things simpler to work with, I'm going to set it up so that the most important columns are to the left. So before I run my experiments, I have an idea of which of the independent variables have the biggest impact on the dependent variable. So what I'm going to do, I'm going to call the most important independent variable A. I'm going to call the second most important B, and the third most important C. All right, now my interactions are going to denote, well, the interaction between A and B is AB. The interaction between A and C is AC. The interaction between B and C is BC. And then the interaction between all three is A, B, and C. And I'm going to set up the columns of my matrix so that the ones that are the most important are farthest to the left. This will help me understand what's going on as I work through this. Now, everything that we're doing here is before I actually do my experiment. I want to make sure everything I do, every little bit of effort I put in, once I start executing my experiments, pays off. And that's the goal of this. Get the most bang for my buck, most bang for my time when I run my actual experiments. Here I'm just setting up to do things better. Okay, so let's take a look at what would be the ideal. If I could have the perfect situation, I would be able to get all of these different observations from my experiment if I had the time, money, and effort. So let's go ahead and say I've got three independent variables, A, B, and C. All right, so I want to show you the matrix that has the intercept, main effects, A, B, and C, my two-way interactions, and my three-way interactions. And I'm going to generate it like this. I'm going to use the expand grid function. So the intercept is, that column is represented with always being a 1. Now the main effects, I'm going to represent with plus or minus 1s. Okay, why am I doing this? In linear regression, I can reduce the standard error of a coefficient's estimate by increasing the spread of the observed values. Okay, well, there's a limit on what's reasonable. So what we're going to do is that this one value represents like a high but reasonable value for A. And this negative one represents a low, when I say low, to the left of the number line, but reasonable value of A. High but reasonable value of B, low, but reasonable value of B, high, but reasonable value of C, low, but reasonable value of C. And so I'm coding it this way. Why do I do this? Because this matrix is going to end up giving me good solid results. Now, when I actually do my linear regression model, it works out. If you go watch my videos on linear regression theory, you'll know that our scaling of our predictor variables actually doesn't change the accuracy of the model. And so what this does for us is that I can use this nice, clean, very beautiful, simple algebraic way of representing my predictor variables. And I don't lose any information by center and scaling my predictor variables in another manner. So what I can do, I can fit my model and then go do a little bit of basic high school mathematics and convert over to the values that are being represented by plus or minus 1. All right, so let's look here. The intercept is all ones. Now the A, you'll notice I'm alternating plus or minus 1 all the way down. B, we do negative twice, positive twice. Negative twice, positive twice. Now for C, it goes negative 4 times, and then positive 4 times. Now the interactions are a little bit trickier to kind of anticipate if you weren't looking at the main effects, but you can see that the column AB is the product of columns A and B. If I go through and just start multiplying, I'll see plus or minus ones. Now the BC column is the product of B times C. All right, so I've noticed that if I go A times B here, I get positive 1. A times B is negative 1. A times B, negative 1. 1 times 1 is 1. Negative 1 times negative 1 is positive 1. 1 times negative 1 is negative 1. Negative 1 times 1 is negative 1. And then 2 positives gives me a positive. And you'll notice the same pattern for B times C. I keep on going through. And I can, A and C get multiplied together, gives me the AC column. And if I multiply all three, I end up getting the ABC column. Okay, so you'll notice that this is a square matrix. All right, so this is an orthogonal matrix, not orthonormal, but it is orthogonal, which is nice. This is exactly what we want. This is like our ideal situation when I have data. So I'm taking the point of view that there's very little data that I can actually generate off of my experiments. Why is that? Because I don't have the funding, I don't have the money, whatever it is. If I could have 8 data points, I would set up that this would be the values of my predictor variable values all the way across. Each row represents the predictor variable values of the experiments. And so what I'm controlling is actually just the A, B, and C columns when I actually run my experiment. I'm just fleshing out the intercept and the AB, AC, BC, ABC interactions just so that we can fully see what's going on. All right, so let's think about this now from like more of an abstract algebra point of view. Notice that I went through and I multiplied entry-wise for each vector. Okay, so I took A times B and I got this column. I took A times C and I got this column. I took B times C and I got this column. All right, it works out, believe it or not, that if I multiply any two of these columns together, I'm always going to get a column that is on this matrix. There are no more that I could possibly get. Okay, well, and now I might be able to get like a column of all negative ones, but that corresponds to the intercept, by the way. So if I have, if it's perfectly correlated with another, it counts for this purpose. Okay, so here are our columns. I can represent it this way. And if I multiply any 2, any 3, any 4, any of these guys together, I'm always going to get a column from this set called G. Okay, so I know that I cannot run all 8 of these experiments. I just don't have the money. I don't have the time. I don't have the resources, whatever it is that blocks me. So I need to do something. So let's say that I've got money for 6 experiments. All right, I can only do 6, but I would like to have all the information I possibly could get. Okay, so what I'm going to do, I'm going to invoke some abstract algebra. Okay, what I'm going to do, I'm going to going to find a normal subgroup that gives me a homomorphism that is very nice in terms of the data point of view. Now, I'm talking about abstract algebra. If you don't fully know it, that's okay. Just know that I'm just invoking some higher mathematics. What I'm going to do is I'm going to say that H is the set E and ABC. And what I'm going to do, every element in this set is going to be functionally mapped to E. All right. Now, why am I calling the intercept E? That's how I learned group theory. My textbook had E for the identity. Notice that if I multiply the intercept column by any other column, I get the other original column back. And so this doesn't change anything. We need this for the purpose of abstract algebra mathematics to work out. So E takes the role of like multiplying by 1 with regular numbers or adding by 0 if I'm doing addition with regular numbers. Okay, so how I'm going to set up my mapping is that I'm going to say, I'm going to take an element from there, I'm going to map it to whatever I get when I multiply everything in H by that element. All right, so every time I have an element, I'm going to walk up, I'm going to multiply it by E, multiply it by ABC, and look at the set that I get. Now, when I say set, remember, order of elements doesn't matter when I talk about sets. Okay, so here's my mapping that I'm going to create. And so first operation, if I take the identity, I multiply by the entire set, then I get the original set back, that's the identity. Now here, f of A, I'm going to take the A element, so I'm taking column A up here, and I'm going to multiply it by E and multiply it by ABC. Well, A times E is going to be the column A times ABC is going to end up being B times C. So remember that this is A times B times C. When I do the multiplication by A, that's effectively A times B times C. Remember that I'm using plus or minus 1. So if I take something and multiply by itself, I always get 1. This is one of the slick things that we do with partial factorial designs, in that here, A times ABC is going to be BC. Remember that if A is multiplied by itself, it becomes all ones. That means it doesn't do anything in the multiplication. All right, so now I see this is the image of A. Now what about B? Well, I take B times the column of all ones, and that's just B. B times ABC, so I have B times A times B times C. Well, this is just going to be AC. C times the set is going to give me C and AB. Boom, look at that. And all this mapping, all this multiplication is just defined by doing multiplication with these columns entry-wise. All right, well, I can keep doing it. I can do it with AB, AC, BC, and you'll notice that I get CAB off of this, which I have right here. When I map AC, I get BAC, which is the same as what I've got right there. And then BC gets mapped to ABC, boom, right there. Look at that. So I can see that f of A is going to be equal to f of interaction between B and C. F of B is going to be equal to the interaction of, or the f of the interaction of AC, and f of C is equal to the image of the interaction of AB. All right. And you'll notice that f of ABC ends up being the same as the image of f of E. So let's go ahead and write that out. Okay, so you'll notice that I have four unique equations. So remember, if I had the money, I would go after 8 different experiments. I don't have the money. So what I've done, I've said, hey, you know what? I can't run everything I want. You know, the world isn't Santa Claus. So what I'm going to do, I'm going to basically sacrifice the three-way interaction because that is the least interesting one. And so what this is going to do, this is going to tell me 4 experiments that I should run that will give me the most information for my 4 runs possible. Okay, so how do I actually use this? All right, what I'm going to do is, you notice that ABC, so the intercept and ABC are both getting mapped to the 1 column. So E is getting mapped to the 1 column. ABC is getting mapped to the 1 column also. So when I do that, I'm going to say, hey, I'm only interested when E is equal to 1, ABC is equal to 1. All right, well, E is always equal to 1, so E is equal to ABC. All right, so now these are the 4 experiments I'm actually going to run. Now, I told you that I have money for 6, but right now I just get down to 4, and that's because of some abstract algebra group theory aspect that so I started out with a size of 8 is like my ideal. My reduction with a homomorphism has to give me either 4, 2, or 1 experiments off of it. And that's just part of how subgroups work with group theory. All right, so here, these are the 4 most important experiments for me to run by this framework of working through. So now, remember that A, B, and C are the aspects I'm going to be controlling. All right, well, I've got 1, -1, -1, -1, 1, -1, -1, -1, 1, and 1, 1, 1. You'll notice that they're all different. And I've got, a pretty good sampling. You notice I've got 2 times A is positive, and 2 times it's negative, 2 times B is positive, 2 times B is negative, 2 times C is positive, 2 times C is negative. All right, so I've got some diversity going on. All right, so this is a pretty good setup off of my limited situation. All right, now, one thing that's going to be not so great about this is that when I walk up and I start analyzing my data after I get it, I know if the true system has a 3-way interaction with the 3 2-way interactions and main effect and intercept, when I look at the intercept coefficient, I know that ABC, the 3-way interaction, is also kind of polluting and throwing things off. That the ones that are equal to each other are going to be confounding. And I won't be able to get a full understanding of it. So when I do this, I'm making the assumption that main effect is like much more important than 2-way interactions. Because when I look at this, I need to be from this point of view, if I'm running this, I have to be able to say the higher order interactions don't really matter. Otherwise, there's nothing I can do. There's nowhere I can go because I have such little data to work with. All right, so let's pretend that this is the actual true situation. That here's the equation of the true result. Here is my dependent variable. I have 3 independent variables of A, B, and C that I have interactions going down the line. And you'll notice I've set it up so that the largest coefficients are to the left and the smaller coefficients are to the right, except for the intercept. But 700 times A, 60 times B, 5 times C, you'll notice that these are the main effects have the largest coefficients of magnitude. Then I get my 2-way interactions, so 0.4, 0.03, 0.002. And then my 3-way interaction is pretty darn small at this point. And I picked 7, 6, 5, 4, 3, 2, 1, just to make this easier to interpret what's up. All right, so I'm going to walk up. I'm going to set up my, let's say that I walked up, I did my experiment. I did these four experiments. Now remember, I don't, the only thing I control are the values of A, B, and C. The interactions take care of themselves. The intercept I don't really control during my experiment. Okay, so now let's say that I've gone and I've done my four experiments. All right, boom, look at that. Okay, so I've got something going on. At this point, I could do a linear regression model. I could start like trying to piece out what's happening. But remember, I told you I had budget for 6 experiments. So now I want to figure out, well, what can I do? Like, I don't want to stop. I can get 2 more off of this. So I need to make those 2 experiments count. Okay, well, I'm going to go through. I do a computation on the averages by A, B, and C. Okay, so here is, if I take it, when A is -1, the average Y is -604. When A is +1, the average is 800 for Y. So here's the average of Y for each constant value of B. So if I set B equal to -1, Y is about 40. If I set B equal to 1, then the average of Y is about 156. If I set C equal to -1, I can see the average of Y is just under 95. And if I set C equal to 1, the average value is about 0.02. Okay, so I'm looking at this and I can see a wider range off of A. I see a wider range off of A. I use the same values in my linear regression. So that tells me that A has a bigger coefficient because of the larger spread in the averages. So this is telling me that A is the most important. Now, in real life, maybe I don't know that A is more important than B, B is more important than C. I won't actually know. I'll have to check the difference in the averages to kind of get an idea. All right, so let's go ahead and let's do this. What I want to do, I want to run some more experiments and I want to get the largest value of Y possible. So let's say that I'm working on a medical trial and I'm trying to increase the target variable, or I'm doing something for finance, or anything that's going on. I'm trying to get the largest Y value possible. And I know that A is the most important. Okay, so let's do this. I'm going to set A equal to 1, and I want it to be the situation where it's an experiment that I haven't already ran. All right, so I'm going to say, hey, I don't want E and ABC to equal each other. I want A to equal 1 because A is the most important and I'm trying to get the largest value possible. Okay, so now this is going to be my next 2 experiments are going to be these 2 right here. All right, so A is equal to 1 both times because I'm trying to maximize A is the most important according to my results thus far. And you can see that I've got B going positive and negative. I got C going negative and positive. So I am getting some diversity in what's going on. I'm going to get a better idea of what's up. Okay, so let's go ahead and let's do this. And here I'm making the assumption that I don't have a perfect mathematical system going on. And here's my new experimental results. After I ran this experiment with these independent variable values, here is my dependent variable value. When I ran this experiment, here is my dependent variable value. Okay, so now I want to actually run my analysis. Here's my full data set. This is all the data that I have to work with. I want to walk up and start doing some linear regression, figure out what's going on. All right, so what would happen if I walked up and I tried to figure out everything off of this? Well, I've got 1, 2, 3, 4, 5, 6 rows of data. The best that I could ever possibly do is estimate 6 parameters. And remember, the intercept counts as a parameter. All right, well, 1, 2, 3, 4, 5, 6, 7 plus 1 for the intercept, 8. There's 8 total. So if I try to estimate this, you'll notice that I get two NAs off of this, one for the three-way interaction, one for AC. Okay, so what I could do, I could go ahead and just trim out the ones that can't be fitted because, I mean, it's stupid to keep them. So first I trim out ABC. And let's see, yeah, so I've got my main effects and then A, B, B, C, and then the intercept is on there. And so now I've got a model going on. I've got 6 points of data, 6 parameters estimated. All right, now notice that A, the real value of A, let's see, where did I put that? I scrolled it. The real value of A is 700 for the coefficient value. That's pretty close. For B, 60 is the true coefficient. That's pretty close. For C, it's 5. All right, so now it's a little bit weaker. It's not as strong as we'd like. And then A, B, and B, C, it's not as strong. But this is, for the amount of data that I've got, this is actually a really good estimate. I was able to get 7 reasonably estimated parameters off of 7 observations. I mean, that's super powerful. Now, this is, a huge advantage for my experiments. I would be able to actually make an inference off of less. Now, a lot of people would not trust this, reasonably so in real life, because there's, they would want to see replicants as much as possible, but sometimes we just can't. Maybe we're working in a field that we are we are trailblazers, and it just takes too much money, too much time to actually accomplish something. This might be the best information possible. All right, so now let's kick it up a notch. Let's kick it up a notch a lot. All right, on this one, I'm going to have another independent variable. We're going to call it D. Okay, and I want to get I want to go and I want to get the matrix built out for this, for me to be able to see the full thing. All right, well, I've got 4 independent variables. It's going to be 2 to the 4, 16 16 by 16 is my full factorial matrix. This is going to be pretty large. Now, as humans, we're not going to really be looking at this, but I want you to see it, and you'll notice the same patterns come up. A, I go plus or minus 1 all the way down. Then B, 2 negative 1s, 2 positive 1s, 2 negative 1s, 2 positive 1s, all the way down. C, I do 4 times negative, 4 times negative. Positive, 4 times negative, 4 times positive. And then D, you'll notice I've got 8 negatives and then 8 positives. And then I have exactly the same system going on. All right, so let's go ahead and say, all right, well, you know what? I want to do the partial factorial analysis. And you know what? Interactions are the least important. So I'm going to sacrifice the 4-way interaction and the BCD interaction also, which is a very reasonable thing to do, but you'd be making a mistake. All right, so it'd be very reasonable to say, you know what, ABC, not that important. BCD, not that important. I put these to the right. 3-way interactions are not as important as main effects or 2-way interactions. And, this is the 3-way interaction without the A. A is the most important main effect. It'd be very reasonable to think this would be a good partial factorial design. Not quite. There's a problem with this. The problem with this is that when I multiply A, B, C, D, this 4-way interaction, by BCD, this 3-way interaction, I end up getting A. If I run this partial factorial design, I'm taking my most important main effect and sacrificing it. And if I run this experiment, I will never be able to recover from this. The data points will still be valid, but I'll have to go and get more experimental runs to be able to get full information. I don't want to do that. Let's go ahead and do a better way. What I want to do, I want to set up that my least important interaction is being mapped to the identity, and I want to figure out a way that I can get my least important one with two lesser important columns. All right, so remember the order that I put things in? A, B, C, D. A is more important to B. B is more important than C. C is more important to D. Off of that mindset, AB is my most important interaction. Okay, so I want to make sure that AB doesn't get in the set that gets mapped. Well, notice that I could take AB times CD would give me the low priority one. Okay, that's not quite the best. I could do a little bit better. A times C times BD gives me ABCD. All right. So now in this mathematics, what I'm doing, I'm sacrificing these two-way interactions, and AC is less important than AB off of the schema that I've presented to you. And so off of this, I've got three elements that are getting mapped to the identity. And you'll notice that if I multiply any two of these together, I'm going to get a third one that's in this set, no matter what. AC times AC is the identity E. BD times BD is the identity. And if I multiply AC times ABCD, that's going to be BD. Like any combination I pick, this is a closed subgroup. All right. So here, when I set up my subgroup for my partial factorial design, I'm saying I'm sacrificing these columns to be able to get more informative value elsewhere. All right. So when I set up this as my set for the subgroup, all of these are going to get mapped to the H image, and then if I multiply each of these by A, then I'm going to get A. Here I get C. Multiply this by A, I get ABD. Multiply this by A, I get BCD. Keep track of the whole matrix setup. That's A times H. And so, I can keep on going down the list. And you'll notice I'm setting it up so that I'll pick up the intercept, A, B, and AB as well as I possibly can. All right, so I'm saying that these four elements need to be mapped to the identity. So to represent that with my matrix, I set each of these, when I filter out my data, I'm going to say, hey, each of these need to be equal to 1. All right, so now here's my reduced data set. So this is my partial factorial design that I have instead of the 16. If I had time, money, and funding and resources and everything I wanted, I would be going for the full 16 by 16 data set with replicants. I'm in a situation, I don't have the time, I don't have the money, I don't have the resources, whatever the case is. So these four are going to be my most bang for the buck situation. And you'll notice when I look at A, B, and C, you'll notice that I'm getting A half the time is positive, half the time is negative. B half the time is negative, half the time is positive. C is half the time positive, half the time negative. All right, so let's pretend that this is the true situation. Now, this is pretty ugly. It's pretty long. And once again, epsilon is just that random normal. Here are the coefficients. I mean, this is kind of long and ugly, but it's okay. All right, so let's say I'm gonna walk up, and these four experiments I'm going to do. So I'm controlling the values of A, B, and C, the intercept and the intercept. Oh, sorry, A, B, C, and D. I control these, and the interactions and the intercept take care of themselves. And here's the results of my four experiments. All right, so let's go ahead and put that into a data matrix. Boom, I've got that. Now, I've got money, let's say, for one more experiment. There's only one more I can do. Okay, so I need to pick what are the values of A, B, C, and D that's going to give me the most bang for the buck. So let's go ahead and say that I'm in a situation that I want to once again maximize Y. I want to maximize my dependent variable. Okay, so let's take a look. So here's something I want you to notice. When I set this up, that, whoops, in this setup, all of these are going to have exactly the same columns. All of these have the same columns. All of these have the same columns. All of these have the same columns. So let's take a look at AC, ABD, BCD. We have A, -1, 1, -1, 1. C, negative, it's alternating back and forth. And we have ABD, where is that? -1, +1. And then it is BCD, alternating back and forth. And it's going to work out that every single time the columns are going to be exactly the same. And so a corollary of that is that if I use a column and take an average of my target variable values, I'm going to get the same average, for the same corresponding values. And so check this out. So AC, ABD, BCD, you'll notice I get the same conditional average values of Y. For BD, ABC, ACD, I get the same values for my conditional values of Y, conditional average. And then AB, AD, BC, CD, I get the same conditional averages of Y. Okay, so let's say that I've got budget for one more trial. All right, well, what could I possibly pick? So first and foremost, I need to figure out what's on the table, what's possible. And so here I'm taking the complement of this restriction. So basically everything that's not in these four is on the table for my next run. I'm not going to replicate something that I've already done. I'm trying to get unique new information. All right. Now with only doing each experiment one time, no replicants, I have to have a lot of faith in every single measurement when I do this. All right, well, so that means if just one of these is not equal to 1, it's in the complement set. So let's take a look at those 12 values. All right, so here are those 12. Now, remember, my goal is to maximize Y. All right, so my goal is to get the largest value of Y I possibly can. So let's just take a look. If I scroll through here, I'll notice that, well, in terms of the main effect, which is what I have control over, when A is equal to 1, I get the most out of it. So let's go ahead and say that A is equal to 1. All right, well, what about B? Well, when B is equal to 1, I get a larger value. When C is equal to 1, I get a larger value than otherwise. I'm comparing these two together. When B is equal to 1, I get a larger value. When C is equal to 1, I've got a larger average. And so I'm going to set A, B, and C equal to 1. And now I've got my last experiment. So I'm going to be running with a total of 5 experiments when ideally I would have 16, and I would have replicants of those 16. All right, well, let's go ahead and say I run my experiment. I set up that in this experiment, A is equal to 1, B is equal to 1, C is equal to 1, D is equal to -1. And we get this value from my experiments. Okay, so now this is my full data set. This is everything that my time, money, and resources will let me do. I need to get as much juice out of this squeeze as I possibly can. Okay, so let's go ahead and run some linear regression. But wait, notice that A and C are equal to each other. Okay, that's not that great. Well, is there anything else like that? Yeah, there is. Because if I see B ends up being equal to ABC. See, D is equal to ACD. So there's a bunch of equalities in here. So if I go and I try to fit the full thing, R spits out a bunch of missing values for the coefficients. There's a whole bunch of them. So let's go ahead and trim this down as much as I can. So I got A, B, D, and AB. All right. I trim that down. I've got 5 estimated values. Okay. Well, remember, I had 5 data points. So I've got some data. I want to make an inference off of this. Well, I know I can't trust the full thing. I don't have enough data for all the ones I want, but what is my interpretation off of these coefficients? What I can do, I can take this matrix here. If I put y to the right-hand side, I can run reduced row echelon form. And cutting off the higher order interactions because we assume that those are the smallest and least interesting, which not ideal, but remember I have too little data to work with. If I do that, if I take these columns here, I run reduced row echelon form, I can run some mathematics. Actually, these columns include the intercept. Always include the intercept. I can see that the intercept, my approximation of the intercept is giving me B naught, the intercept value, plus these two interactions. The coefficient for A is giving me the coefficient of A plus the coefficient of B. Coefficient of B is giving me the coefficient of B plus interactions. Coefficient of D is giving me the coefficient of D plus interactions. And my one interaction term is a combination of interactions. All right, so this is not ideal. If I walk up, so notice that I have 5,002. All right, so that's my intercept. You'll notice that if I take AC plus the intercept plus BD, or is it plus 1, that's pretty close to my estimated coefficient. If I take the estimated value of A, which is almost 1,600, well, that's going to be 9 plus 7,000 approximately. You can see that the estimated value of A is actually giving me these two coefficients together. My B hat, close to 8,000. Well, that is, this is a little bit less than 8,000. You'll notice that we've got some subtraction going on. I found this out by doing reduced row echelon form, and I threw away the higher order terms for the approximation because we make the assumption that higher order interactions are not as important. And then D hat is estimating beta D plus plus some interactions. And then my two-way interaction coefficient is estimating a combination of them. So this is not the full information I would want, but this at least gives me something to work with. If I have some theoretical knowledge, let's say I know about like the ratio of the A coefficient and the C coefficient just from theory, I can estimate what each of those values are reasonably so. So, remember, I did all this with very, very, very little data and made something work. This is very, very powerful. All right, partial factorial design is really cool because I get to invoke abstract algebra and I get a lot of information, a lot of bang for my buck without having to do a heck of a lot. If I could only run a few experiments, partial factorial design does a good job of setting it up so I understand the results that I have, like all of this. I mean, it's ugly, it's not ideal, but if I'm in that situation, I can at least figure something out. I've got the most bang for my buck. I've got the deepest understanding I possibly can. All right, well, that's all I've got for you. Life is short. Do math.